Hello again, everyone. Welcome to our discussion of section 2.4, where we will talk about graphical symmetry. In other words, sometimes when we graph functions, there are a certain category of functions that are symmetric with respect to the origin of the axis or the Cartesian coordinate system. There are some that are symmetric with respect to the y-axis, and there are some that are symmetric with respect to the x-axis, and we're interested in these functions. Okay, before we cover this material, I wanted to remind all of you to please read through section 2.4, spend no more than 45 minutes on it, preferably half an hour to 45 minutes, then watch the video and attend class. And then as you attend class or watch the video, take notes on questions that you might have, or the important things, or the things that you think are important to you as you listen to the lectures or watch the video. And then complete all the homework assignments by the due date. And of course, please spend at least half an hour each week, not every day even, each week, to review the previous material in order to keep everything fresh in your mind. Okay, so section 2.4, we begin by a brief description of how the symmetry might occur, or how we can predict it. Okay, there is a way, even though the symmetric nature of these graphs is graphical, but it's numerically we can predict it. We don't have to graph them. There's a numeric way of finding out whether they're symmetric with respect to the origin, with respect to the y-axis or x-axis. Here's a brief description of that. If you have a function where if you replace y with negative y in an equation, then produces the same equation, then the graph of that equation is symmetric with respect to the x-axis. Okay? That's easy to remember. That's how I remember these. So if the y replaced with minus y produces the same equation, then the equation must be symmetric with respect to the other axis, x in this case, right? So this is one example of such an equation. So we replaced y in this equation with minus y, like that, and after simplifying we get the same equation. So the graph of this equation is going to be symmetric with respect to the x-axis. Number two, if replacing x with minus x in an equation produces the same equation, then the graph is symmetric with respect to the y-axis. So this is again easy to remember. If it's the x that you replace with negative x produces the same equation, then the graph of that equation is symmetric with respect to the other axis, which is y. Okay. Now, if we replace x with, and that's an example of that, basically. So here we replaced x with minus x and squared it, just like that, just like what this is saying. And we ended up with the same equation. Compare this with that. Even after replacing it with negative x, we ended up with the same equation. So the graph of this equation is symmetric with respect to the y-axis. Now, if we replace x with minus x and y with minus y in an equation produces the same equation, then the graph is symmetric with respect to the origin. And this is an example of that. So you can actually, on a scratch paper, just disregard what I have, start with this, and replace x with negative x and y with negative y, and simplify, see if you get that. Okay, and I'm trying to log into computers so I can show you these things on Desmos calculator. That way I think you'll get a better understanding of what this is talking about. But that's just one way of determining symmetric nature of equations in this case, because they don't have to be functions as long as there are some equations. So the computer is up. Let me switch to, I'm going to graph these. I'm going to graph this one, and this function, so you can see what we're talking about when we talk about the symmetric nature of these equations with respect to the y, x, and the origin. Okay, let me, as I switch to the computer, you might see the screen blank out for a second. Don't mind that, please. It's just what it does as I switch. Okay, so you should see that screen now. So let's go to Desmos calculator. Okay, so I'm going to graph that first one, which was x squared plus y to the fourth power equals 5. Okay, so this is the graph of this equation. It's definitely not a function, right? We know that if any geometry or mathematical entity fails the vertical line test, it's not a function. So this is not a function, but it's a mathematical entity. It's an equation of some kind. Okay, and so this was the first case that I had on the worksheet. So here, if you replace the y with negative y, you will end up with the same exact equation as before. So this graph is symmetric with respect to the x-axis. By the same token, actually, I should have used this for the other symmetric, for number 2 on the worksheet as well, because if you replace x with negative x, you get the same equation too. So this equation is symmetric with respect to both the x-axis and the y-axis. Okay, it just occurred to me looking at my worksheet, I could have just used that example as something that is symmetric with respect to both axes. That's also possible. And also with respect to the origin, right? This is if you replace x and y at the same time with negative x and negative y, you get the same equation. So this mathematical entity is actually symmetric with respect to the origin as well. So it's symmetric with respect to all of those, x-axis, y-axis, and the origin. So let me then, in that case, I guess, so yeah, so let's graph this one also. Y equals x squared plus 2. Oops, I don't know how that happened, but x squared plus 2. Okay, so this is clearly symmetric with respect to the y-axis, right? But definitely not symmetric with respect to the x-axis, right? It doesn't even touch the x-axis. So if you replace the x with negative x, you get the same, and simplify, you get the same equation back which means the equation is symmetric with respect to the other axis, y. Okay, so this is an example of that. I wanted to show you all these examples so you have a picture to associate it with these words that are on the worksheet. Once again, as I switch back to the dock camera, the screen is going to blank out. Okay, so now you should be okay. All right, so now continuing on with what we have here. The other aspect of symmetric nature of functions, if we have even functions and odd functions. So even functions are symmetric with respect to the y-axis. And more important than that is how we determine if a function is even or odd. So if this happens, a function is even. Very important, and also for the odd functions. Okay, and I guess we have examples of this, but after I go over this with you, I'm gonna, on a piece of scratch paper here, I'm gonna go over a couple of examples to make sure that you follow what, oh, it's right there actually. So I can talk about it here. So if the graph of a function is symmetric with respect to the y-axis, we say that it is an even function. So numerically, this is how we can show that. This is how we can show that a function is even and therefore symmetric with respect to the y-axis. So simply, in this function, replace x with minus x. What do you see? So we have function at negative x. So I replaced x with negative x. And then simplify. What do we get? X squared. So f at negative x is equal to x squared. F of x is equal to x squared. Right? So we replaced the x with negative x and we ended up with the same function. So this function is an even function. We already know, we already knew from this discussion that it would be symmetric with respect to the x-axis, y-axis, right? Because we replaced x with negative x. So we knew this function would be symmetric with respect to the y-axis. But what we didn't know, and now we are introducing that, is that such a function that is symmetric with respect to the y-axis is called an even function. Okay? If you replace the x with negative x, you get the same function. In trigonometry, that you'll use this a lot, and then again and again in higher calculus classes, you'll use the concepts of even and odd functions a lot. But here is the place we introduce it. So by the time you get there, you already know about this stuff. Okay? Then, if the graph of a function is symmetric with respect to the origin, right? So for even functions, the symmetric nature of the function happens, or graph happens with respect to the y-axis. That's for even functions. For odd functions, the symmetric nature happens of the graph happens with respect to the origin. Okay? And here's an example of such function. So what happens with the odd functions? If you replace the x with negative x, you end up with a function that is the negative of the previous function. So the original function was f of x. You replaced x with negative x, you ended up with minus f of x. So that's an odd function. What is an example of such a function? Right there, the cubic function. Let's replace x with negative x. Okay. What do we get? We get negative x cubed, but this odd power is not going to, it's going to preserve the negative, right? It's not going to cancel it out like raising this to second power would. If this was 2, that negative would drop out, right? But this is an odd number. 3 is an odd number, so that negative is preserved. So we end up with minus x cubed. Compare this with the original function. So f at negative x is equal to minus the original function, which is x cubed. Visually compare these two, this one and that one. The function at negative x is equal to minus of the original function, which was f of x. If you multiply this by minus 1, you get the function at negative x. And that's what it's saying. For odd functions, if you evaluate x, the function at negative x, you get minus of the original function, minus 1 times the original function, which is that, minus x cubed. Compare that with x cubed, right? Okay, so here it says determine if the graph is symmetric with respect to the x-axis, the y-axis, or the origin. So this should not take you even a minute. So please pause the video, take a minute, write down your own solution for each one. State with respect to either x-axis or y-axis or the origin, which one of those is any of these graphs symmetric to. Okay? So I'm assuming you've done that. Now here, looking at this is symmetric with respect to the y-axis. With respect to the y-axis, right? How about this one? This is symmetric with respect to the origin. Like that, origin. How about this one? It's symmetric with respect to the x-axis. Right? How about this one? Symmetric with respect to the origin. And that's the famous graph, the graph of the famous function, the cubic function, right? So, and we know the cubic function is symmetric with respect to the origin. Okay, so next it says graph each equation that follows and determine visually if the graph, not numerically, right? There is numeric way of determining whether an equation is symmetric with respect to the x-axis, the y-axis, or the origin. There's a numeric way of doing that. And there's also a graphical way of doing that. So this is saying graph it and show that graphically. So it's like this exercise, but we have to draw the graph. It's not been provided to us. Okay. Oh, by the way, they say then verify your visual assessment algebraically. We'll do that too. Okay, so they're asking for both actually. All right, so what I will do is replace x with negative x and see what I get. Do I get the original equation or not? Okay, so negative x squared plus 4 equals 3y. Well, I started here, which is okay. I'll draw it graphically too. Then simplifying this, what do we get? We get x squared plus 4 equals 3y. So what happened is I replaced x with negative x and I got the original function back. So this graph is going to be symmetric with respect to the y-axis. Okay, so because of that, graph is symmetric with respect to the y-axis. So let's draw it. We're going to pick some values, right? We're going to pick some easy values, right? Let me put that here. I'm going to pick some easy values such as minus 2. And so this is x. These are y values. Let me pick minus 2. Minus 2 if x is minus 2, minus 1, 0, 1, 2. I think these 5 values should be enough to graph that. So minus 2 squared is positive 4, plus 4 is 8. 8 equals 3y, so y equals 8/3. 8 over 3. If x is negative 1 squared, so that'll be 1 plus 4 is 5. 5 equals 3y, right? So solving for y would be 5 divided by 3. If we substitute for x with 0, we get 4 equals 3y. And then solving for y would be 4 divided by 3. If you substitute 1, you get again 5/3. For 2, again, we get 8/3. Okay, so obviously this is an even function. Okay, so let's graph this. These numbers are a little bit awkward. These are fractions, but I think we can make them work. So when x equals minus 2, that would be here. Y is 8/3. 8/3 is a little bit over 2, right? Let's see what it is exactly. So 8 divided by 3, 2.7, let's say. Okay, so this is 2.7. How about 5 over 3? That'll be 1 point something, right? 5 divided by 3, 1.7. 4 divided by 3, 1.33 or 1.3. And again 5 over 3, which is 1.7. Again 8 over 3 is 2.7. So you pick some easy x values and you calculate the y, and now let's plot these. Minus 2 comma 2.7, that would be roughly here somewhere. Let me put that dot here. Minus 1 comma 5/3, so that would be minus 1 comma 1.7 right there. At 0, 1.3, so right there, right? And my points are small because these, I don't want things to smear or like that. So that's better a little bit. So those are the 3 points. And then 1 comma 5/3 is again a little bit higher. So 1.7 right there, right at the same level as that one. And then 2 comma 2.7, it'll be the same level as that over 2. Okay, so roughly this graph is going to look like this. Something like that. Like this, like that. Okay, and you can see that the graph is symmetric with respect to the y-axis. And of course, if it doesn't look like that, it's because my drawing skills are not that great. But on a computer, you could see that those two arms are located in a symmetric way with respect to the y-axis. So we've shown this graphically by picking some easy values, and we've also shown it numerically by picking x to be minus x and seeing that we end up with the same function as before. Okay. And please pause the video and work on this, and then once you have your own solution, and then come back to the video. So we're going to do the same thing. This time let's graph this. So first, and then we'll check this out numerically as well. So we have some easy numbers. Let's say if we have, I have an idea what this looks like. It's going to have two pieces actually, not one, because it's very similar to the function, the graph of the function 1 over x. So this is minus 4 over x. So it's going to be flip-flopped, maybe in the second and the fourth quadrant. Let's see. So if x is, say, -1, I'm picking easy numbers. Minus 4 divided by minus 1, that's positive 4. If 0 is out of the question, right? 0 is not an option there. And if it is, say, -2, another easy number, minus 4 over minus 2, that's positive 2. And then if it is 1, then we have minus 4. And if we have 2, we have minus 2. Let's pick another easy numbers. Let's say 4 and -4, right? So if x is -4, then minus 4 over minus 4, that's positive 1. If it's positive 4, then it's -1. I think this should give us a fairly decent number of points to graph this function. Okay, -1, 4. Well, let's use my red pen here. -1, 4. That's that, right? That's that point. -1, 4. All of these are points we're going to graph like that. Okay. So -1, 4. That's 1 point. -2, 2. That would be that point. And 1, -4. That one. 1, -4 right here. 2, -2. That would be here. -4, 1. -4, 1, like that. Yeah, as expected, it's got two pieces, and it is going to be symmetric with, well, let's wait and see. And 4 and -1, that one. Okay, so because this function cannot accept x value equal to 0, so we would expect to see this behavior, this split, and then also that there's an asymptotic behavior as the graph line approaches 0, x value 0 on either side. So as the line is coming from this side, it's approaching 0, right? 0 along the x-axis. And you can see this asymptotic behavior shoot up like that. Okay? And as we go this way, again, as we approach x value 0, or even y value 0, the graph exhibits asymptotic behavior. So the graph ultimately is going to look something like this. Like this, and then it's going to curve like that and behave asymptotically towards the x and y axis, and also the same behavior on this side. Okay, like that. Okay, so that's manually, we've done that. What can you say about this graph in terms of, with respect to which of those entities, origin, x-axis, or y-axis, is it symmetric? Is it symmetric with respect to the x-axis? No. Is it symmetric with respect to the y-axis? No. Is it symmetric with respect to the origin? Yes. Right? With respect to the origin, it is symmetric right there. So symmetric with respect to the origin. Okay, so now they've asked us to show this numerically. How do we show this? Or algebraically, sorry. It says algebraically, not numerically, right? It said, verify your visual assessment algebraically. So algebraically is when we replace x with, let's say, negative x. Right? Do we get, so with respect to the origin, well, in this case, this is how we would do it. We would do it rather using the even-odd function. Okay, because this is an odd function. So let's show that this is an odd function. Let us show that this is an odd function. And the emphasis on odd because odd functions are symmetric with respect to the origin. So let's replace x with negative x. Y equals minus 4 divided by, instead of x, negative x. Right? What do we end up with? We end up with y equals positive 4 over x. So this is, if we call this function f of x, let's call it f of x equals negative 4 over x, right? If that is f of x, then what I just did here would be, let me correct this with my thicker pen, f at negative x. So we replace, you can barely see it up here, we replace x with negative x, right? That's what we did. Now what did we get? We get positive 4 over x. And let me also correct this y with negative x. Okay, that's better. So if you multiply, now look at this original function. If you multiply minus 4 over x by minus 1, right, you get f at minus x. So we've shown that the function is odd. So therefore, or thus, f, the function f at negative 6 is equal to minus that. So the function is odd. Oops, let me straighten that out. So the function is odd. A lot of this is very, very visual. So, I'm not talking about the graph only. Obviously, the graph is visual, but I'm talking about how the functions change as you replace x with negative x. Visually compare what happens to these symbols. So, we started with f of x equals minus 4 over x, right? That. We replaced the x with negative x here. What did we end up with? 4 over x. But 4 over x is minus 1 times minus 4 over x. So if you multiply minus 4 over x by minus 1, you get 4 over x, which is the result of replacing x with negative x. So visually compare these, and you'll see how replacing x with negative x is equal to as if you multiply the original function f of x with a negative 1. That's what this showed, that these two are equal with each other. And when this happens, we have an odd function. Okay? So this is visual not only graphically, but also symbolically. Look what happens visually to this function when you replace x with negative x. What happens to the function visually? Okay, compare them visually. Okay, so determine algebraically, that means with the method like that, replacing x with negative x, determine algebraically whether the graph is symmetric with respect to the x-axis, the y-axis, or the origin. So please, once again, pause the video, answer these two questions on your own, and then come back to the video. This exercise, even if you're not fully feeling completely comfortable with this, should not take you should take you between 10 to 15 minutes. And I'm saying if you're feeling uncomfortable, it should take you that much. If you're feeling comfortable with this, you should be done in like 2-3 minutes. You should be done. Okay? So, determining algebraically, I'm assuming you've done that, and now you have your solution in front of you. Which means, algebraically, so let's replace x with negative x, right? And see what happens. Y cubed equals 2 times minus x squared. Now let's simplify this. We end up with y cubed equals 2x squared. We ended up with the same function, right? This, even after replacing x with negative x, we end up with the same function. So this function is symmetric with respect to the y-axis, right? So we have the same function, so symmetric with respect to the y-axis. Okay. Now, on the other hand, if you replace y with negative y, do you get the same function? No. So this function is not symmetric with respect to or this equation is not symmetric with respect to the x-axis. Okay. So here, I mean, as you do this, ahead of time, visually plug these, plug minus x, plug minus y into these variables visually, and with your mind see if what happens if you do that. Do you get the same function or not? Okay, so you build anticipation that will then you can verify with your calculation. That's always a good idea, because if your calculation doesn't match your anticipation or expectation, then you might have an error numerically, or your expectation may not have been completely correct. Okay, so here, before even we do anything numeric, right, or algebraic, if I know that if I plug in negative x for this, I'm going to end up with the same thing, but negative x here will not give me the same thing. Okay? It will not give me the same equation. So this is not symmetric with respect to the y-axis. Do you see what I mean? I'm just visually plugging in negative x here, and obviously with this power 2, negative x is going to be the same term is going to result, even if you plug negative x here. But you have another x here, and if you replace this with minus x, that's going to change the equation, so you're not going to get the same equation. One of the terms is even, the other term is not. So the combination is odd function, or the combination is not even, we can say. We can't say it's odd, but in fact it's not odd, but the combination is certainly not even. But visually, if you plug in for negative x, or for x with negative x, and for y and x with negative x and negative y, you get the same result. You get the same equation. This is what I'm talking about. So, and I'm saying do this because then you build expectation for what you need to do, and you'll save yourself time. If you don't do this, then you'll end up plugging in for x with negative x, and you don't end up with any result that would match, that would be symmetric with with respect to the x-axis, y-axis, or anything. And then you would try plugging in for these variables for x with negative x and for y with negative y, which would give you the same result, the same equation. So building expectation helps you save time, and also if you don't end up with that expected result, it helps you go back, or it helps you go back and check your work, which is always a good idea. So let me do that. Let me do both. So I'm going to replace x with negative x, right? Let's see what happens. So when we do that, we end up with negative x, right, times y minus x squared equals 3. So we want to know if after replacing x with negative x, we get the same equation. So let's simplify. We get minus xy minus x squared is x squared equals 3. Almost, but not quite, right? The 3 and the 3. Negative x squared, negative x squared. But here, xy minus xy. So no. So not the same equation, right? So not the same equation as the original one. Not the same equation as the original. Okay, so inconclusive. So let's replace x with negative x and y with negative y. Let's see what happens. We're going to do that here. Replace x with negative x, y with negative y. So we're going to do both at the same time. Well, so we have negative x times negative y minus x squared equals 3. So minus x times minus y, positive xy, minus x squared equals 3. Is this the same equation as that? Absolutely. It is, right? Same equation. The same equation as the original equation. So the graph is symmetric with respect to which one? Do you remember? We had that on the first page, right? Let me bring it back. It's the last one right here. Number 3. If replacing x with negative x and y with negative y in an equation produces the same equation, then the graph is symmetric with respect to the origin. So to the origin. Okay. So that one was symmetric with respect to the y-axis, this one, the part A. And part B is symmetric with respect to the origin. I hope things are beginning to make sense. Okay, so here it says determine visually whether the function is even, odd, or neither even nor odd. So let's remind ourselves what is an even function, to which entity it is symmetric. So it's any even function is symmetric with respect to the y-axis, right? We had it on the sheet earlier. How about the odd functions? So that's for even functions. For odd functions, are symmetric with respect to the origin, right? Take a look at this. This is certainly an even function, right? Even. It's symmetrical with respect to the y-axis. If you fold this graph along the y-axis, it'll superimpose or overlap on the other side. How about this? This is symmetric with respect to the origin, right there. If you fold this graph on the origin, along the origin, that piece will fold over this, and the rest of this will fold over that. So this is odd function. As a matter of fact, in trigonometry, if that course is part of your study program, you will see that this is the sine function, that's the cosine function. And the cosine function is famous for being an even function, and the sine function is famous for being an odd function. Okay, so determine algebraically whether the function is even or odd or neither. So we know how to do this, right? This is the criteria that we need to use. It was the definition of even odd functions were on the first page again. Let me bring this back. So this is how we determine if a function is even or odd. We substitute x with negative x. If we end up with the same function, that function is even, like that. If we replace x with negative x and we end up with a function that is the product of -1 and the original function, then that function is odd. Okay, so I've given you two examples, each of which is one of the most famous examples of the relevant function. X squared is a famous even function, and x cubed is a famous odd function. Okay, so here, let's do that. Before doing that, please pause the video. Finish all three, A, B, and then C also here, and then come back to the video. And I think that will be worth your time in a sense that it'll be very productive. These videos will be very productive if you approach them that way, that you always solve these examples before you see my solutions. Okay, so now let me replace x with negative x and see what happens. Okay, let's simplify. This is still f, the function at negative x. So this is the result. So is this the same as the original function? Absolutely not, right? That's 7x cubed, this is minus 7x cubed, so no. So right away you can tell that not even. Not even. So is it odd? If it is odd, then f at negative x should be equal to -1 times all of that. Compare this with -1 times all of that. Let me bring my scratch paper here. So here's the function. I'm going to write it first. So okay, So this is what I mean. This is the original function. If we multiply this function by -1, that is -1 times f of x. What do we get? We get -7x cubed minus 4x plus 2. That's -1 times f of x. Is that equal to f at -x? The function at -x? We just found that out. F, the function at -x, is that, which is this. So let me bring this down. So -7x cubed minus 4x and minus 2. Compare these two. This and that one. Are they the same? The first term, yes. The second term, yes. How about the third term? No. Because of the third term, negative function of x, negative f of x, is not equal to function at -x. These two, if these two are equal, then you have an odd function. But if they're not, just like what I've shown, the third term is not equal. The first two terms are, not the third term. So we do not have an odd function either. Not odd. So it is in fact neither. Neither is the correct answer here. It's neither even nor odd. Now this one. Let's replace x with -x. So f with that, and this is the third root of -x. Because it's the third root, this minus can come out. So we have minus third root of x. So what have we shown here? Look, compare visually again. Compare these symbols. F of x is equal to third root of x. The function f of x at -x is minus third root of x. So because of these two, because of this, compare that with this, we can say that f of x is equal to minus well, I should have said this way. I should have said minus. Let me put that. So minus that, minus 1 times this, is equal to that. So this is an odd function. Right? If you multiply the original function f of x by -1, which is what I've shown here, and if that's equal to the function evaluated at -x, which it is, then you have an odd function. That's what this first page said. That's what the definition of an odd function. See? Function at -x is equal to -1 times the function. If that happens, you have an odd function. And that's what we showed here. Okay, so we have an odd function. This one, let's replace x with -x. So what do we end up with? We end up with -x squared is x squared. So now visually compare the f of x with this, f at -x. Are they the same? They're the same. So because of these two, we can say that f of x is equal to the function at negative x. Okay, we had the original function, we replaced x with negative x, and we ended up with the same function. So this meets the definition of an even function. An even function is symmetric with respect to the y-axis. Odd function is symmetric with respect to the origin, right? But they're not asking us for the symmetric nature of this. They're just asking which one is odd, which one is even. So I'm not going to write that down. But we know even functions are symmetric with respect to the y-axis, and odd functions are symmetric with respect to the origin. Well, we've come to the conclusion of another section. Thank you for persisting through these videos. Please remember, even if I forget to mention it, please remember to pause the video every time I get to an exercise in these videos. Solve the problem on your own, then unpause the video to see my solutions. And that will be the most productive way of watching these videos. So for now, have a nice day, and I'll see you all again next time.